Remember those math competition problems that seemed totally impossible? Well, the new AI on the block, Seed Prover, is tackling the hardest of them all from the International Mathematical Olympiad. And it's not just getting by, it successfully proved 5 out of 6 problems at the 2025 competition. So what's its secret weapon? It doesn't try to solve the entire monsters proof in one go. Instead, it smartly breaks the problem down. First, it generates and proves a bunch of smaller helpful facts called lemmas. Think of it as finding all the puzzle pieces before putting the whole picture together. Once it has these confirmed lemmas, it uses them to construct the final proof. It's a deep and broad reasoning strategy that's changing the game. Ready to see how this digital mathlete does it? Let's dive in.
Let's dive into the abstract of our paper, Seed Prover. Deep and broad reasoning for automated theorem proving. We start by acknowledging the impressive progress large language models, or LLMs, have made in mathematical reasoning. They use reinforcement learning and long chains of thought to solve problems. But when it comes to theorem proving, they hit a wall. Why? Because natural language doesn't offer clear supervision. This is where domain-specific languages like the Luoxin system come in handy. The Luoxin system provides precise supervision through formal proof verification, making it easier to verify correctness. This paper introduces Seed Prover, a reasoning model that refines proofs using feedback from the Luoxin system, proved lemmas, and self-summarization. It's designed to handle complex contest problems with innovative inference strategies, enabling both deep and broad reasoning. Seed Prover excels by solving a high percentage of formalized International Mathematical Olympiad (IMO) problems, outperforming other models on benchmarks like Mini-F, 2F, and Putnam Bench. And to tackle the Luoxin system's limitations in geometry, we introduce Seed Geometry, pushing the boundaries in formal geometry reasoning. Together, these systems demonstrated their prowess at the IMO 2025 by fully proving most problems. Look at Figure 1 here. It highlights the growth and performance on the Mini-F2F test, showcasing the trajectory of theorem-proving capabilities over the years. Now let's explore the introduction. We see how LLMs have expanded reasoning capabilities through natural language, especially evident in math benchmarks. But training these models to verify answers is tricky. Every step needs careful correctness checks. Enter formal languages like the Luoxin system, which offer a way to verify proofs without ambiguity. Remember how AlphaProof solved some IMO problems? That's a testament to these languages' power. We have 2 types of theorem provers here: step level, breaking proofs down line by line, and whole proof generation models, which take on proofs more holistically. Seed Prover falls into the latter category, combining long reasoning chains with formal verification. It has 3 standout features: lemma-style proving to generate useful intermediate steps, iterative proof refinement with the Luoxin system, and a unique resource allocation strategy for deep problem solving. Given the Luoxin system's limited geometry capabilities, Seed Prover includes seed geometry, excelling by filling in missing geometry elements and rapidly solving problems. This sets the stage for understanding how Seed Prover and seed geometry work together to tackle complex mathematical challenges, especially in geometry. Moving on, we delve into the advanced features of seed geometry, a significant upgrade over Tong geometry. First, it extends the domain-specific language by streamlining cumbersome ruler and compass construction steps. This simplification is particularly handy for complex geometric actions, like those involving triangles and circles. Next, seed geometry enhances performance with a backend rewritten in C++, giving it a massive speed boost compared to the Python version. This upgrade facilitates deeper searches by efficiently managing memory and exploiting compiler optimizations. Then, we see the exceptional LLM that seed geometry employs, fine-tuned on vast datasets of coding and mathematics. It uses a policy approach to generate problem-solving proposals without a separate value model. The extensive search process is fascinating. Seed geometry transforms new problems into a canonical form and uses beam search to generate proposals. If one leads to a solution, the problem is solved. This setup supports distributed processing across GPUs, allowing parallel reasoning and inference. It's a clever way to tackle complex problems while minimizing computational overhead. Here we dive into Seed Prover's unique approach using Luoxin 4. The standout feature is its lemma-style proving. Unlike traditional methods that tackle proofs as a whole, Seed Prover breaks them into smaller, manageable lemmas. This strategy helps track which parts have been proved and which need more work. Lemmas are modular, meaning they can be handled independently and used flexibly across various problems. Look at figure 2 here. It shows a comparison between a whole proof and a lemma-style proof, breaking down the proof into smaller, independent parts for easy combination. Next, let's talk about conjecture proposing. This involves exploring potential properties of a problem without rushing to a full solution. Seed Prover is trained to suggest useful conjectures, like properties of functions, that might guide the reasoning process. This approach is about opening up broad exploratory searches over the problem space, crucial for solving complex math challenges. It's about exploring possibilities and generating insights that could eventually lead to a solution. Diving into the workflow and training strategies for Seed Prover, look at figure 3. It visualizes how problems are approached through different inference settings. In whole proof generation, problems are tackled by generating lemmas and attempting full proofs, interacting directly with the lean compiler. If a proof fails, the system adjusts and tries again. The light and medium inference settings introduce more layers of refinement, allowing the model to work through multiple attempts and incorporate new contexts. Training involves a multi-stage reinforcement learning approach for seamless interaction between Seed Prover and the Luoxin system. It gradually increases problem difficulty and maximizes output length as training progresses. The system uses various inputs, like hints and summaries of previous attempts, to enhance adaptability. During test time scaling, strategies are based on available computational resources. The light setting allows for multiple refinements, solving complex problems within a manageable time frame. The focus is on iteratively refining proofs and maximizing efficiency, enabling Seed Prover to handle problems beyond single-pass approaches, setting the stage for innovative problem solving. Let's explore the heavy inference setting of Seed Prover. Look at figure 4. This setting is all about handling complex problems needing deeper exploration. It starts with a conjecture pool, generating thousands of potential conjectures to cover all angles of a problem. During inference, Seed Prover aims to prove or disprove each conjecture. Successful ones refine proof attempts further. The heavy inference setting focuses on depth, understanding intricate problem details. Medium inference balances depth with breadth, incorporating both outer and inner refinements to handle complex proofs. The outer refinement improves the main proof, while the inner one targets specific lemmas. This setup uses a budget for detailed exploration. Light setting focuses on correcting syntax errors and refining initial proof sketches. This multifaceted approach allows Seed Prover to tackle a variety of problems, from simpler ones to those needing thousands of proof lines. The page concludes with examples of Seed Prover solving difficult problems under different inference settings, showcasing its adaptability and power in problem solving. Now let's talk about large-scale problem generation using Seed Geometry's backend. By collecting data from past geometry problems, the team generated over 230 million unique problems. They used a policy model to estimate remaining steps and a value model to assess the current state. But the value model struggled with accuracy, prompting a shift to step-by-step generation with beam search for final evaluations. Look at Table 1 here. It shows Seed Geometry's strong performance, outperforming its predecessor, Alpha Geometry 2, in solving difficult IMO geometry problems. Seed Geometry solved 43 benchmark problems, setting a new standard in automated geometry problem solving, particularly excelling in proof-based problems. This advancement underscores Seed Geometry's capability to handle complex challenges, paving the way for more effective problem-solving strategies in mathematical proofs. Let's look at some performance evaluations for Seed Geometry and Seed Prover. Check out Table 2. It shows how Seed Geometry consistently outperforms Alpha Geometry 2 across IMO shortlist problems, highlighting its superior capability in handling complex geometry challenges. Then, Table 3 shifts focus to Seed Prover, comparing it to previous state-of-the-art systems across several benchmarks. Metrics reveal that Seed Prover matches or exceeds prior models, especially in tasks like Putnam Bench and Mini F2 F-Test, showing high accuracy and reliability. When Seed Prover was evaluated at the IMO 2025 contest, problems were translated into formal statements, and initial solutions were AI generated before human translation. A model used both medium and heavy inference settings to tackle unsolved problems. Impressively, Seed Geometry solved certain problems almost instantly, while Seed Prover derived proofs under time constraints. This evaluation illustrates Seed Prover's adaptability and effectiveness, highlighting its potential impact on solving diverse mathematical problems efficiently. Finally, Let's evaluate Seed Prover's performance across past International Mathematical Olympiad problems. It shows impressive results with a high success rate. Using a dataset from comp files and Mini F2F, Seed Prover effectively tackles easy to medium problems. In Mini F2F, Seed Prover demonstrates outstanding accuracy, solving most problems, even those that are challenging when formalized. In Putnam Bench, it proves most problems, indicating strong performance compared to traditional methods. Combi Bench evaluations highlight Seed Prover's strength in algebra, but also its struggle with combinatorics. In Mini CTX version 2, Seed Prover showcases its ability to generalize across diverse real-world mathematical problems, achieving a notable success rate. The conclusion emphasizes seed geometry and Seed Prover's capabilities in formal reasoning, accelerating verification processes, and effectively solving complex problems. These systems offer a more cost-effective and reliable solution compared to human experts. The future work aims to further integrate formal systems with LLMs for enhanced problem solving. Thanks for joining us today. Happy exploring together!